Tonight, we drift into the quiet mysteries of the universe. You don't need to follow every word. Just let the story carry you, like starlight across a calm sky. As your thoughts begin to settle, imagine yourself floating in the vast emptiness between stars, where silence reigns absolute, uninterrupted for eons. In this perfect stillness, this complete absence of sound, we begin our journey. In the deepest reaches of space, silence isn't merely the absence of noise, it is a presence unto itself, a canvas stretched across the cosmos. The vacuum between stars holds no molecules to carry vibrations, no medium through which pressure waves might travel. It is a silence more complete than any we could experience on Earth, where even in our quietest moments, blood pulses through our veins and breath moves softly through our lungs. Space knows a deeper quiet. Imagine drifting through this perfect stillness, where light travels unimpeded for billions of years. Stars shine their ancient light, galaxies spiral in slow, majestic arcs, and planets trace their orbits, all in perfect silence. The dance of the cosmos unfolds without a whisper, a ballet performed without music, yet perfect in its choreography. This is the natural state of the universe, serene, undisturbed, eternal in its quietude. Yet within this vast silence, energies gather, forces coalesce. The universe, for all its peaceful appearance, harbors tremendous power beneath its tranquil surface. Like a sleeper whose dreams grow increasingly vivid, the cosmos stirs with invisible currents of energy, magnetic fields stretching across light years, gravity bending the very fabric of space, radiation streaming in all directions from sources almost too powerful to comprehend, and sometimes, very rarely, these energies concentrate. They focus and build until the universe itself can no longer contain them. Then, in a moment that defies our earthly understanding of scale, these energies release. Not with a bang, for there is no sound, but with a fury that, if translated into our terrestrial experience, would overwhelm all senses. It is not heard but felt, not seen directly but witnessed in its effects as they ripple across space and time. One such event occurred in a distant corner of our galaxy, far from the quiet blue world we call home. It was not the first of its kind, nor will it be the last, but it stands as perhaps the most powerful single release of energy humans have ever detected since we first began looking up at the stars and wondering what might lie beyond our atmosphere. This is the story of a whisper that shook the cosmos, a silent roar that, despite occurring over 50,000 light-years away, reached across the void to touch our world, reminding us of the incredible forces that shape our universe. If you were to travel to this distant place, a journey that would take you far from the familiar spiral, arm of the Milky Way where our sun resides, you would find yourself approaching a region near the constellation Sagittarius, toward the dense center of our galaxy. Here, amid fields of stars and clouds of cosmic dust, resides an object so extraordinary that it challenges our understanding of physics. It appears as nothing to the naked eye, invisible in the traditional sense, yet its presence is unmistakable to the sensitive instruments we've designed to detect the universe's more exotic phenomena. This object, designated SGR 180620, belongs to a rare and fascinating class of celestial bodies known as magnetars. They are in essence the remaining cores of massive stars that have lived their bright, brief lives and died in spectacular supernovae. But unlike most stellar remnants, which fade into obscurity as cooling embers, magnetars retain a fearsome power, a magnetic field of almost incomprehensible strength. Consider for a moment the magnetic field of Earth, the invisible force that guides compass needles and creates the auroras that dance in polar skies. It is a gentle presence, a whisper of energy that shapes our world in subtle ways. Now imagine a magnetic field a quadrillion times stronger. That's one followed by 15 zeros. Such a field would be powerful enough to erase every credit card on Earth from halfway to the moon. It could distort the atoms in your body from thousands of miles away. It is a force so intense that it defies easy comparison to anything in our everyday experience. This is the quiet power of SGR 180620, sleeping in the depths of space. For most of its existence it slumbers, containing its vast energies within a sphere no larger than a city, perhaps 12 miles across. Imagine the mass of our sun, compressed into a volume you could fit within the boundaries of Manhattan. This incredible density creates a world where the conventional rules of physics begin to bend and transform. On its surface, gravity is so intense that a marshmallow would hit with the force of 1,000-pound weight. Its magnetic field is so powerful that it warps the very quantum nature of the vacuum surrounding it. Yet, for all this power, for all this exotic physics, SGR 180620 remained largely unknown outside specialized fields of astronomy. It was simply one more strange object in a universe filled with wonders. A curiosity studied by a relatively small group of scientists interested in the extreme physics of neutron stars and their magnetic cousins, the magnetars. That is, until a December day in 2004, when this sleeping giant stirred and, in doing so, sent a message across 50,000 light-years of space. That would cause astronomers around the world to reconsider just how powerful such objects could be. As we continue our journey through this cosmic tale, imagine yourself drifting closer to this remarkable object, moving through the perfect silence of space toward a power that defies imagination. Feel the gentle pull of curiosity drawing you forward, even as the immensity of what lies ahead inspires a quiet awe. There is no rush in this exploration, no urgency, only the patient unfolding of a story written in starlight and gravity, in magnetic fields and radiation, in the dance of forces that shape our universe. Let your mind float freely as we approach this sleeping giant, this magnetar whose brief awakening would send ripples through the scientific community and remind us all of the tremendous energies that lie dormant in the night sky. Allow yourself to be carried along by the currents of this narrative, just as light itself is carried across the vast emptiness between stars, steadily, silently, inevitably, illuminating what was once unknown. The path to understanding begins, as so many scientific journeys do, with a moment of unexpected discovery. And to appreciate what happened when SGR 180620 awakened, we must first understand what it is, and how such an extraordinary object came to exist in our galaxy. In the soft glow of twilight, as the first stars begin to appear in the evening sky, imagine looking up and seeing not just the familiar pinpricks of light that have guided travelers for millennia, but truly understanding what they are: enormous fusion reactors balancing the inward pull of gravity against the outward push of nuclear fire. Stars, those seemingly eternal beacons, live lives of their own. They are born from clouds of gas and dust. They mature through long periods of stable burning, and eventually they die. Some stars, similar in mass to our Sun, end their lives relatively quietly, shedding their outer layers in beautiful planetary nebulae, leaving behind dense cooling cores called white dwarfs. Others, far more massive, face a more dramatic fate. When these stellar giants exhaust their nuclear fuel, the delicate balance that has sustained them through millions or billions of years suddenly tips. Gravity, that patient force, finally overcomes the pressure of fusion, and the star collapses. What follows is among the most energetic events in the universe, a supernova explosion, where the outer layers of the star are blasted outward, at speeds approaching 1/10 of the speed of light. For a brief moment, a single dying star can outshine an entire galaxy of billions of stars. The elements forged in the star's core, carbon, oxygen, silicon, and heavier elements up to iron, are scattered into space, enriching the interstellar medium, eventually to be incorporated into new stars, new planets, and perhaps even new forms of life. But what of the core? In stars of sufficient mass, the collapse continues beyond what normal matter can withstand. Electrons are forced into atomic nuclei, combining with protons to form neutrons. The pressure becomes so extreme that all that remains is a sphere of neutrons, a neutron star, with a density so high that a teaspoon of its material would weigh billions of tons on Earth. And here, in this realm of extreme physics, we find the origins of our magnetar. Most neutron stars already possess powerful magnetic fields, spinning rapidly and emitting beams of radiation that, if they sweep across Earth, we detect as regular pulses, hence the term pulsar. But a small fraction of neutron stars develop magnetic fields that are hundreds or thousands of times stronger than typical pulsars. These are the magnetars, and SGR 180620 is among the most powerful ever discovered. How does a magnetar form such an incredibly strong magnetic field? The exact mechanisms remain an area of active research, but astronomers believe it likely involves the conservation of magnetic flux during the collapse of the parent star, combined with an effect known as the dynamo mechanism, where the rapidly rotating, highly conductive material of the newborn neutron star amplifies the initial magnetic field to extraordinary levels. Imagine the final moments of the massive star that would become SGR 180620, perhaps 40,000 to 50,000 years ago. As measured in Earth time, a blue supergiant many times more massive than our Sun reached the end of its life in a remote region of the Milky Way. Its core, having fused lighter elements into progressively heavier ones, finally produced an iron core, a stellar dead end, as iron fusion consumes rather than releases energy. In less time than it takes to draw a single breath, the star's core collapsed from a size roughly similar to Earth to a sphere perhaps 12 miles in diameter. The outer layers, suddenly unsupported, fell inward, then rebounded off the incompressible neutron core with unimaginable force, creating a shockwave that tore through the star's envelope and launched it into space in a brilliant supernova explosion. The remnant core, now a newly formed neutron star, found itself rotating hundreds of times per second. Its magnetic field lines wound and compressed into a configuration of exceptional power. The conservation of angular momentum, the same principle that makes a spinning ice skater rotate faster when they pull in their arms, ensured that as the core shrank, its rotation speed increased dramatically. Similarly, the magnetic field, compressed into a much smaller volume, intensified to levels that defy easy comprehension. Thus was born SGR 180620, a magnetar with a magnetic field estimated at over 1015 Gauss, about a quadrillion times stronger than Earth's magnetic field, and even 1,000 times stronger than a typical neutron star. This newborn cosmic powerhouse, spinning rapidly in the aftermath of its violent birth, settled into what appeared to be a semi-stable state. Occasionally, small adjustments in its crust, starquakes, analogous to earthquakes, but occurring on a surface. Where mountains might be mere millimeters high due to the intense gravity, would release bursts of gamma radiation. These occasional flares caused astronomers to classify the object as a soft gamma repeater, hence the designation SGR. But for many years, it seemed to be just one more exotic object in a universe filled with wonders. Little did they know that this particular magnetar was building towards something far more dramatic, an event that would rewrite scientific understanding of just how powerful such objects could be. As you continue to drift through this cosmic narrative, feel the gentle rhythm of stellar evolution, birth, life, death, and transformation playing out across the canvas of our galaxy. These processes, though violent beyond human scale, unfold with a patience measured in millions and billions of years. There is no rush in the cosmos, no hurry as gravity and nuclear forces play their ancient game of push and pull, of creation and destruction. Let your mind rest in this space between moments, in the quiet aftermath of a supernova and the slow evolution of a magnetar's tremendous magnetic field. Allow yourself to settle into the stillness that follows creation, the peace that comes after violence has subsided and new forms emerge from the remnants of the old. In this pause, this cosmic breath, we find SGR 180620 waiting, its energies building, its future momentarily dormant but inevitably active once more. For decades, the magnetar remained relatively quiet, occasionally releasing small bursts of gamma radiation as its crust adjusted and magnetic field lines shifted. Astronomers studied these minor eruptions with interest, learning more about the strange physics of these extreme objects. But nothing in these routine observations prepared them for what would happen on December 27, 2004, a day when the sleeping giant truly awakened. On that winter day, as people around the world went about their daily lives, celebrating holidays, working, sleeping, living their terrestrial existences, largely unaware of the dramas unfolding in deep space, SGR 1806-20 underwent a sudden, catastrophic adjustment. The exact trigger remains uncertain, but astronomers believe it likely involved a major shift in the magnetar's crust, a starquake of unprecedented scale that allowed the twisted, strained magnetic field lines to reconfigure themselves explosively. Result was a giant flare, a sudden release of energy so intense that it saturated the detectors on every space-based observatory designed to monitor such events. Gamma-ray detectors on satellites were overwhelmed within a fraction of a second, their instruments temporarily blinded by the sheer intensity of radiation streaming from this distant point in our galaxy. Imagine sitting in the quiet control room of a space observatory, monitoring the steady stream of data from distant satellites. Screens display the usual patterns of cosmic background radiation, the occasional spike from a solar flare, the steady signals of known pulsars. Then, without warning, every display spikes simultaneously. Alarms sound as backup systems activate. For a brief moment, you might wonder if something has malfunctioned. In the equipment itself, surely no natural source could produce such an intense burst of radiation. But as secondary confirmations come in from other observatories around the world and in space, the truth becomes clear: this is real. Something truly extraordinary has occurred thousands of light years away. An event so powerful that even across that vast distance, it has momentarily overwhelmed our most sensitive detectors. This was the experience of astronomers on that December day, as they witnessed the arrival of radiation from what would later be recognized as the most powerful magnetar flare ever recorded, an event so extreme that it forced scientists to reconsider the upper limits of energy release possible. From such objects, the initial spike of hard gamma rays lasted less than a second, about 0.2 of a second to be more precise. But in that brief moment, SGR 1806-20 released more energy than the Sun emits in 250,000 years. If you were to capture all the energy our Sun has produced since the Roman Empire, it would roughly equal what this magnetar released in the blink of an eye. Following this initial, blindingly intense spike, the magnetar continued to emit a more prolonged tail of emission, gradually decreasing in intensity over the next several minutes. This extended emission, though far less powerful than the initial spike, still represented an extraordinary release of energy, like the aftershocks following a major earthquake, but scaled to cosmic proportions. The burst was so powerful that it had measurable effects on Earth's upper atmosphere, despite having traveled more than 50,000 light-years from its source. The gamma rays and X-rays ionized the outer layers of our atmosphere, causing changes detectable by very low-frequency radio monitoring stations. For a fleeting moment, the influence of this distant magnetar was physically present in the protective shell around our own world. More dramatically, the burst of radiation was powerful enough to bounce off the surface of the Moon and be detected again by instruments in Earth orbit, like a cosmic echo, returning to our detectors after reflecting from our nearest celestial neighbor. This single burst of energy, originating from an object just miles across, had illuminated our local cosmic neighborhood with a brilliance that defied conventional understanding. As data from various observatories and satellites was compiled in the hours and days following the event, astronomers began to grasp the true scale of what they had witnessed. This was not merely another interesting magnetar flare, it was something unprecedented, a cosmic event that pushed at the boundaries of what theorists had considered possible. The energy released in those fractions of a second was enough to power the entire United States for 1,000,000 years. If converted to sound waves at Earth's distance, it would have been the equivalent of 10 billion fire alarms blaring simultaneously from 10 feet away. If SGR 1806-20 had been within 10 light-years of our solar system rather than 50,000, the flare would have caused a mass extinction event on Earth, stripping away our atmosphere and bathing the planet in lethal radiation. Let that scale settle into your mind as you continue to drift through this narrative. The universe operates at magnitudes that can seem almost abstract in their enormity, forces so vast that we can only understand them through mathematics and analogy rather than direct experience. Yet these forces are as real as the ground beneath your feet, as real as the gentle rhythm of your breathing. As you listen to these words, there is a certain peacefulness in contemplating such power from a safe distance, like watching ocean waves crash against a distant shore from the comfort of a warm, secure vantage point. We can appreciate the raw energy, the primal force, without being threatened by it. In the case of SGR 1806-20, we are fortunate observers, close enough to detect and study this remarkable event, yet far enough away to be unharmed by its tremendous power. As news of the giant flare spread through the astronomical community, scientists around the world turned their attention to SGR 1806-20. What could they learn from this unprecedented event? What might it tell them about the physics of magnetars, about the extreme conditions that exist in these remarkable objects, and what implications might it have for our understanding of other energetic cosmic phenomena? One of the most intriguing aspects of the event was that despite its tremendous power, it produced no sound whatsoever. In space, where there is no medium to carry sound waves, even the most violent explosions occur in perfect silence. The vacuum between stars swallows all possibility of sound, leaving only the silent language of light, radiation, and gravitational waves to carry information across the void. If the giant flare had occurred within Earth's atmosphere, the energy release would have created the loudest sound ever experienced in human history. A roar so intense that it would have been heard around the globe, shattering windows, toppling buildings, and causing widespread destruction through sheer acoustic pressure. Yet in the vacuum of space, this immense release of energy was completely silent, a contradiction that highlights the strange physics of our universe. Imagine witnessing such an event from a theoretical spaceship at a safe distance. You would see a sudden, blindingly bright flash of light, primarily in wavelengths invisible to human eyes, though some would register in the visible spectrum. You might notice your ship's electronic systems temporarily disrupting as the wave of radiation passed through your vessel. You might feel a slight warmth as some of that energy was absorbed by your craft's hull, but you would hear nothing, only the quiet hum of your ship's life support systems, the soft sound of your own breathing inside your helmet, perhaps the beating of your heart as you witnessed one of the most powerful events in the cosmos. This silence in the face of such power creates a cognitive dissonance, a gap between what we know intellectually and what our senses are equipped to perceive. It reminds us that the universe operates according to principles that often differ from our everyday experience, that the cosmos exists independent of our ability to directly sense it. Much of what happens in the universe is beyond our unaided perception, too vast, too distant, too energetic, or simply informs that our evolutionary history has not prepared us to detect directly. Yet through the tools of science, our space-based observatories, our mathematical models, our collaborative research efforts, we can extend our perceptual reach beyond these natural limitations. We can detect gamma rays that would be lethal if experienced directly. We can measure magnetic fields billions of times stronger than anything we could survive. We can calculate energies so vast that they defy easy comparison to terrestrial scales. In a sense, modern astronomy allows us to safely witness cosmic violence from afar, translating the extreme into the comprehensible, allowing us to experience through data and imagery what would destroy us if encountered directly. There is a certain poetry in this, in our ability to know what we cannot directly experience, to understand what we cannot physically survive. As you continue to float through this narrative space, consider the strange beauty of this contradiction. The loudest non-sound ever recorded, the most powerful event we never heard. Feel the peaceful contrast between the extreme energies we're discussing and the quiet moment you're experiencing now. There is room for both in our understanding. The violent and the gentle, the explosive and the still, the distant power and the present peace. The flare from SGR 1806-20, traveling at the speed of light, had taken approximately 50,000 years to reach Earth. When the original stellar explosion occurred, early humans were still developing their first complex tools. The light from this event had crossed a significant portion of our galaxy, passing countless stars and nebulae, traversing vast empty regions of space, all while human civilization emerged, developed, and eventually created the tools necessary to detect and understand such distant phenomena. There is something humbling in this realization that we are witnessing events not as they are happening now, but as they happened in a distant past. The universe we observe tonight is not the universe that exists tonight, but rather a complex tapestry of different time periods, with each distant object showing us a different moment in cosmic history. As we continue our exploration of this remarkable event, let your mind drift along these rivers of time and space, flowing gently through the cosmos, connecting the distant past with the present moment, the tremendous power of a magnetar flare with the quiet contemplation of a human mind trying to comprehend it. In this connection, this bridge of understanding across the vast gulfs of space and time, We find a unique form of cosmic harmony, a quiet reminder that we are part of this universe, not separate from it, capable of understanding even those aspects of reality that lie far beyond our direct experience. The giant flare from SGR 1806-20 lasted only moments in human perception, but its effects continue to ripple through scientific understanding even today. In those brief instants, this distant magnetar provided data that would keep astronomers, physicists and theorists engaged for years, challenging existing models and expanding our understanding of what's possible in the extreme environments found throughout the cosmos. To truly grasp the scale of what occurred, we need to look more closely at the physics involved, at what happens when magnetic fields of such extraordinary strength suddenly reconfigure themselves. The surface of a magnetar is unlike anything we can easily imagine. It exists in a state where quantum effects, normally only relevant at subatomic scales, become macroscopically important. The magnetic field is strong enough to distort the shapes of atoms, stretching them into elongated cylinders rather than their normal spherical distributions. In such an environment, the distinction between different states of matter begins to blur. The surface is believed to form a type of crystal lattice of iron nuclei immersed in a sea of electrons that have been partially constrained by the intense magnetic field. Above this surface, the magnetosphere, the region dominated by the star's magnetic field, contains highly energized particles trapped in magnetic field lines, similar to Earth's Van Allen radiation belts, but unimaginably more intense. When a starquake occurs on the surface of a magnetar, these carefully arranged structures are suddenly disrupted. Magnetic field lines, which had been wound and strained like enormous cosmic rubber bands, suddenly reconnect in new configurations, releasing their stored energy in the process. This magnetic reconnection is similar to what occurs in solar flares on our own sun, but scaled up to energies billions of times greater. The released energy accelerates particles to near the speed of light, generating intense beams of radiation, primarily in the form of gamma rays and X-rays. These high-energy photons stream outward in all directions, carrying the signature of the cataclysmic magnetic event across the vastness of space. Some portion of this energy, after traveling for 50,000 years, eventually reached our solar system on that December day in 2004, triggering instruments designed to monitor such cosmic messengers. But the story doesn't end with the initial detection. In the days, weeks, and months following the giant flare, astronomers continued to study SGR 1806-20 with every available instrument. They watched as the magnetar settled back into a new equilibrium state, still occasionally emitting smaller bursts as its crust and magnetic field continued to adjust after the major event. Radio telescopes, which had not initially detected anything unusual from the magnetar, began to pick up an expanding bubble of radio emission in the weeks following the flare. This radio afterglow, caused by particles ejected during the flare interacting with the surrounding interstellar medium, provided additional clues about the nature and strength of the original event. By studying how this radio emission evolved over time, astronomers could work backward to better understand the energetics of the giant flare itself. One of the most fascinating discoveries came from analyzing the precise timing and energy spectrum of the radiation from the giant flare. The data revealed quasi-periodic oscillations, subtle, regular patterns in the intensity of the emission that provided clues about what was happening on the magnetar's surface. These oscillations, occurring hundreds of times per second, were interpreted as seismic vibrations on the magnetar's crust, actual starquakes that continued to resonate through the ultra-dense material after the initial major rupture. By studying these seismic vibrations, analogous to how geologists study earthquakes to learn about Earth's interior, astronomers gained unprecedented insight into the internal structure of a neutron star. The frequency and pattern of these oscillations helped confirm theoretical models about the composition and stiffness of neutron star crusts, providing a rare glimpse into the physics of matter under conditions impossible to recreate in Earth-based laboratories. Other researchers focused on the implications of the giant flare for different astrophysical mysteries. Some suggested that similar magnetar flares, if occurring in distant galaxies, might account for a portion of the short gamma-ray bursts that had puzzled astronomers for decades. These brief but intense flashes of gamma radiation, previously thought to result exclusively from neutron star mergers or black hole formation, might in some cases be magnetar giant flares in distant galaxies, cosmic imposters mimicking the signatures of even more catastrophic events. As you continue to drift through these scientific explorations, notice how each discovery leads to new questions, how each insight opens doors to further mysteries. Science progresses not in a straight line, but in an expanding web of connections, with each new data point adding texture and depth to our understanding. There is a natural rhythm to this process, a gentle back and forth between observation and theory, between what we see and how we interpret it. In this rhythm, there is room for uncertainty, for provisional understanding, for the humility of recognizing that our knowledge is always incomplete. The story of SGR 1806-20 and its giant flare is not a tale of absolute certainty but of increasing clarity, a gradual refinement of our understanding. Through careful observation and thoughtful analysis, let this awareness of the provisional nature of knowledge rest easily in your mind. There is no need for absolute conclusions, for definitive statements that might later need revision. Instead, we can appreciate the current best understanding while remaining open to new discoveries that might shift our perspective in unexpected ways. This openness is not a weakness of scientific understanding, but its greatest strength, the capacity to grow, to evolve, to better approximate the complex reality of our universe with each new observation. As the initial excitement about the giant flare subsided and the data analysis progressed, scientists began to consider more deeply what the event might tell them about the fundamental forces at work in our universe. The magnetic fields generated by SGR 1806-20 are among the strongest, known to exist in nature, approaching the theoretical maximum possible before the vacuum itself would become unstable. In such extreme magnetic environments, many of our familiar physical laws begin to behave differently. Quantum electrodynamics, the theory that describes how light and matter interact, predicts that sufficiently strong magnetic fields can affect the behavior of the vacuum itself, potentially allowing processes like photon splitting, where a single gamma ray spontaneously divides into multiple lower-energy photons. These quantum effects, normally only relevant in the most extreme conditions, become important in understanding the physics of magnetars. Moreover, the sheer energy involved in the giant flare raised questions about the maximum possible energy that could be stored and released in magnetic fields. How had the magnetar accumulated such tremendous energy? What determined the timing of its release? Could even more powerful flares occur under different conditions? These questions pushed theorists to refine their models of how matter and energy behave in the extreme environments found around neutron stars. Some researchers saw in the giant flare an opportunity to test theories of gravity. The intense release of energy should, according to Einstein's general relativity, have generated gravitational waves, ripples in the fabric of space-time itself that propagate outward at the speed of light. While the gravitational wave detectors of 2004 were not sensitive enough to detect such signals from a source as distant as SGR 1806-20, future observations of similar events with more advanced detectors might provide new tests of gravitational theory under extreme conditions. Beyond these scientific implications, the giant flare also served as a cosmic reminder of our planet's place in a dynamic and sometimes violent universe. Earth exists in a relatively quiet corner of the galaxy, sheltered from many of the more energetic phenomena that occur closer to the galactic center or in regions of active star formation. Our Sun, a stable, middle-aged star, provides a relatively consistent environment that has allowed life to evolve and flourish over billions of years. Yet, events like the giant flare from SGR 1806-20 remind us that the cosmos is capable of unleashing energies far beyond anything in our everyday experience. We are, in many ways, fortunate observers, positioned at a safe distance from the more extreme events that occur throughout our galaxy, yet equipped with the intelligence and technology to detect and study these phenomena from afar. Imagine, for a moment, if Earth had been significantly closer to SGR 1806-20, perhaps within a few light-years rather than 50,000. The consequences would have been catastrophic. The intense burst of gamma radiation would have stripped away our protective ozone layer, allowing harmful solar ultraviolet radiation to reach the surface. The direct effects of the gamma rays themselves would have triggered complex chemical reactions in the atmosphere, potentially producing compounds harmful to life. In the most extreme case, if Earth had been in the direct path of the most intense portion of the beam, the energy deposited could have been sufficient to trigger mass extinction. This is not merely speculative. Some scientists have suggested that past extinction events in Earth's history might be linked to nearby gamma-ray bursts or magnetar flares, cosmic accidents where our planet happened to be in the wrong place at the wrong time as some distant stellar catastrophe directed its energy in our direction. While such hypotheses remain difficult to prove definitively, they highlight the interconnectedness of cosmic processes, how events occurring thousands of light years away can potentially influence the delicate balance of life on a small, blue planet orbiting an unremarkable star in a quiet spiral arm. As you consider these cosmic scales of distance and energy, of potential threat and actual safety, allow yourself to feel both the awe of such tremendous forces and the peace of knowing that in this moment, we exist in a protected space, distant enough from such extreme events to study them safely, to learn from them without being harmed by them. There is a certain cosmic perspective that comes from understanding both our vulnerability and our good fortune in the face of such powerful natural phenomena. Let your thoughts drift gently between these scales, from the unimaginably powerful forces at work in a magnetar to the quiet safety of the Earth's current position, from the violent reorganization of magnetic field lines in a distant neutron star to the peaceful rhythm of your own breathing as you absorb this cosmic tale. In this movement between scales, between the extraordinary and the ordinary, we find a unique form of meditation, a contemplation of our place in a universe that operates at magnitudes both far smaller and far larger than our everyday experience. Now, having explored the immediate impacts and scientific implications of the giant flare, let us turn our attention to the heart of the magnetar itself, to the exotic physics that makes these objects among the most extreme environments in our universe. What conditions exist at the core of SGR 180620? What strange states of matter persist in its ultra-dense interior? How does it maintain the incredibly powerful magnetic field that gives it its distinctive properties? To understand a magnetar, we must first grasp just how compressed the matter within it truly is. A typical neutron star, including magnetars, packs roughly 1.4 times the mass of our Sun into a sphere perhaps 12 miles in diameter. This creates a density almost beyond comprehension, approximately 100 million tons per cubic centimeter. To put this in more relatable terms, a teaspoon of neutron star material would weigh approximately 1 billion tons on Earth, about as much as a small mountain. At these densities, normal matter cannot exist. The pressure is so intense that electrons are forced to combine with protons, forming neutrons, hence the name neutron star. The result is essentially a giant atomic nucleus, held together by gravity rather than the strong nuclear force, composed primarily of neutrons, with a small proportion of protons and electrons. The interior of a neutron star is believed to be structured in layers, like an exotic cosmic onion. At the very center, where pressures reach their maximum, even neutrons may be compressed beyond their normal state, potentially breaking down into their constituent quarks. This hypothetical state, known as quark matter or strange matter, represents one of the most extreme forms of matter possible in our current understanding of physics. Surrounding this potential quark core is a sea of neutrons in a superconducting, superfluid state, behaving as a fluid with zero viscosity and perfectly conducting electricity. This superfluid neutron sea makes up the bulk of the neutron star's interior. Above this lies a crust, relatively thin compared to the star's radius, composed of increasingly heavy atomic nuclei, arranged in a crystalline lattice as you move inward. Immersed in a sea of free electrons, in a magnetar like SGR 180620, this already exotic structure is further influenced by the incredibly strong magnetic field. The field affects the motion of charged particles, constrains certain quantum processes, and introduces asymmetries into what would otherwise be a nearly perfectly spherical object. The magnetic field likely penetrates throughout the magnetar, with complex geometries that can store tremendous amounts of energy in their configuration. The surface of a magnetar exists in a realm where quantum effects become macroscopically relevant. The magnetic field is strong enough to cause atoms to distort into cylindrical shapes, aligned with the field lines. It affects the propagation of light in ways that create distinct polarization signatures. It constrains the movement of charged particles into tight spirals around magnetic field lines, creating beams of radiation that sweep through space as the star rotates. Gravity at the surface of a magnetar is approximately 100 billion times stronger than on Earth. This creates an environment where the concept of falling takes on new meaning. An object dropped from a height of 1 centimeter above the surface would hit with the same energy as a nuclear explosion. The escape velocity is roughly half the speed of light, meaning that only the most energetic particles can escape the magnetar's gravitational pull. In this environment of extreme density, extreme gravity, and extreme magnetism, even the vacuum behaves differently than it does in our everyday experience. Quantum theory tells us that the vacuum is not truly empty, but filled with virtual particles that briefly pop into existence and then annihilate each other. In the intense magnetic field of a magnetar, these quantum fluctuations can be affected, potentially allowing processes like vacuum birefringence, where the vacuum itself becomes directionally dependent in how it transmits light. Consider for a moment the strangeness of a place where the very emptiness of space has properties, where the nothing between particles becomes something with measurable effects. This is the realm of the magnetar, a place where our intuitive understanding of physics breaks down, where the theoretical meets the actual in ways that challenge our most sophisticated models. As you contemplate these exotic conditions, allow yourself to appreciate both their scientific fascination and their philosophical implications. The existence of magnetars demonstrates that the universe is capable of creating conditions far more extreme than anything we can reproduce in laboratories, serving as natural experiments that test the limits of our physical theories. In studying objects like SGR 180620, we are essentially observing physics at its frontiers, seeing how matter and energy behave when pushed to their limits. At the same time, there is something philosophically profound about the existence of such objects. They remind us that what we consider normal physics, the rules that govern our everyday experience, represents only a tiny island of conditions in the vast ocean of what is possible. Most of the universe exists in states very different from what we directly experience, operating according to the same fundamental laws, but expressing them in radically different ways. Let this awareness settle gently into your consciousness, the recognition that the familiar is not the norm but the exception, that the universe is stranger and more varied than our limited experience might suggest. There is both humility and wonder in this perspective, a quiet acknowledgement of how much there is to learn, how many states of being exist beyond our direct experience, yet remain accessible to our understanding through the tools of science and mathematics. In this space of contemplation, of peaceful engagement with the exotic and the extreme, we find ourselves connected to the universe in its full diversity, not just the comfortable, familiar aspects that support our existence, but also the wild, intense expressions of the same physical laws that manifest in places like SGR 180620. This connection, this recognition of our place within the full spectrum of cosmic possibilities, offers a unique form of cosmic perspective, a viewpoint that encompasses both the gentle and the extreme, the nearby and the distant, the familiar and the exotic. After the tremendous energy release of the giant flare, SGR 180620 gradually settled into a new equilibrium state. The magnetic field, having partially unwound itself through the violent reconnection event, established a slightly different configuration. The crust, having undergone the equivalent of a magnitude 23 earthquake, on a scale where the largest Earth earthquakes barely exceed magnitude 9, gradually stopped resonating with seismic waves. The storm of particles that had been accelerated to near light speed dispersed into the surrounding space, carrying with them the signature of this momentary cosmic fury. In the aftermath, silence returned, the perfect silence of space, unbroken by the soundless explosion that had, For a fraction of a second, outshone almost everything else in our galaxy. The magnetar continued its slow rotation, completing one turn approximately every 7.5 seconds. Its powerful magnetic field once again contained, restrained, holding its energy in temporary reserve. This return to quiescence, this restoration of cosmic calm after a moment of extreme activity, follows a pattern common throughout nature. Systems build up energy gradually, release it suddenly, then return to a state of relative equilibrium, often slightly different from their previous state. We see this in earthquakes, in solar flares, in thunderstorms, and in magnetar giant flares, a rhythm of accumulation, release, and recovery that plays out across vastly different scales and systems. There is something reassuring in this pattern, this cosmic cycle of tension and resolution. It suggests a certain balance, a natural process of adjustment and adaptation that occurs throughout the universe. Energy is rarely contained forever. It finds expression, release, transformation. The forms change, but the underlying patterns reveal a cosmos that, for all its occasional violence, tends toward equilibrium, not static and unchanging, but dynamically stable, continually adjusting and evolving. As SGR 1806-20 returned to its quiet rotation, the energy released in its giant flare continued to travel outward at the speed of light. Like ripples spreading from a stone tossed into a pond, the electromagnetic pulse propagated through space in an expanding sphere, encountering planets, stars, nebulae, and other cosmic structures as it went. Most of this energy simply passed through the vast emptiness between stars, never interacting with matter, destined to continue its journey indefinitely, perhaps until the expansion of the universe itself stretches the wavelengths beyond any practical possibility of detection. But some portion of this energy encountered interstellar gas and dust, causing atoms to ionize, molecules to dissociate, dust grains to heat slightly before cooling back to their ambient temperature. In this way, the magnetar's flare left subtle imprints on the interstellar medium, faint records of its occurrence preserved in the temporarily altered states of the matter it encountered. These alterations, though minor from a cosmic perspective, represent the physical memory of the event, inscribed in the chemistry and energy states of the matter that fills the space between stars. This concept of cosmic memory, of events leaving traces that persist long after the events themselves have concluded, offers another perspective on the interconnectedness of the universe. Nothing happens in true isolation. Everything affects something else, even if only slightly. The giant flare from SGR 1806-20, though brief in duration, created changes that will persist in various forms for thousands or millions of years. Some of these changes are directly measurable, like the radio afterglow that astronomers tracked for months following the event. Others are more subtle, detectable only in principle rather than in practice with our current technology. Still others exist as information, patterns of radiation carrying the signature of the event outward through space, potentially detectable by civilizations, around distant stars if they happen to be looking in the right direction, with sufficiently sensitive instruments. As you contemplate this ongoing journey of the magnetar's energy through space, imagine following a single photon, a particle of light emitted during the giant flare. This photon, traveling at the universal speed limit of 186,282 miles per second, moves outward from SGR 1806-20 in a straight line. It passes through vast empty regions, occasionally encountering an atom of hydrogen or helium, the sparse gas that fills even empty space. Most of these encounters result in no interaction. The photon simply continues on its path, unaffected. After years of travel, our photon might pass through a nebula, a cloud of gas and dust where new stars are forming. Here it might be absorbed by a dust grain, momentarily heating it, before being re-emitted in a different direction, and often at a different wavelength. Or it might ionize an atom, knocking loose an electron that goes on to affect other nearby atoms. In this way, the information carried by the photon, its energy, its direction of travel, its polarization, becomes transformed, integrated into the complex interactions of matter and energy within the nebula. Decades or centuries later, that same energy, now redistributed and transformed, might contribute to the gentle pressure that helps shape the nebula. perhaps slightly influencing the formation of new stars or planetary systems. The original photon no longer exists as a discrete entity, but its effects continue as part of the nebula's ongoing evolution. This is how information persists in the cosmos, not necessarily in its original form, but transformed and integrated into new patterns, new structures, new possibilities. The giant flare from SGR 180620 is in this sense not truly over. It continues to exist as alterations in the state of the universe, as energy that has been redistributed but not destroyed, as information that has been transformed but not erased. Let your mind follow these ripples outward, these expanding spheres of influence that begin with a single event and extend potentially throughout the observable universe. There is a peace in this perspective, a recognition that nothing is truly lost, only transformed, reconfigured, expressed in new forms. The energy released by the magnetar, though no longer concentrated in a brilliant flash, still exists, still shapes the cosmos in subtle ways that extend far beyond the original event in both space and time. In this gentle expansion of perspective, this following of consequences beyond the immediate and obvious, we find another layer of cosmic connection, a recognition that events are not isolated moments, but nodes in an ever-expanding web of cause and effect, of transformation and integration. The story of SGR 180620's giant flare doesn't end with the return to quiescence. It continues in every subtle alteration that the released energy creates as it journeys outward through the cosmos. As we follow these ripples of influence, these expanding spheres of cause and effect, we might also consider another aspect of the giant flare, how it appeared to us, how it translated its electromagnetic signature into something we could comprehend with our human senses. The radiation from SGR 180620 arrived primarily as gamma rays and X-rays, forms of light far beyond the range of human vision, carrying energies that would be lethal if experienced directly. To study this radiation, scientists had to transform it, not just detect it with specialized instruments, but convert it into forms that human minds could interpret and understand. The raw data from gamma-ray detectors and X-ray telescopes was processed, analyzed and often visualized as graphs, spectra, or false color images that translated the invisible into the visible, the directly undetectable into the comprehensible. One particularly fascinating translation involved converting the timing patterns of the radiation into sound. By taking the variations in intensity that occurred at frequencies within the range of human hearing, roughly 20 to 20,000 cycles per second, and mapping them to audio frequencies, scientists created a way to hear the giant flare, not as it would have sounded since it produced no actual sound, but as a sensory representation of its temporal structure. The result was an eerie, complex audio pattern, beginning with a sudden, intense burst of noise corresponding to the initial spike of hard gamma rays, followed by a more rhythmic, pulsating section representing the oscillations in the tail of the emission. These oscillations, caused by seismic waves rippling through the magnetar's crust, created a sort of cosmic drumbeat, the actual vibrations of an object 50,000 light-years away, translated into a form that human ears could perceive. This sonification, this translation of data into sound, represents a bridge between human experience and cosmic phenomena. We cannot directly sense gamma rays or X-rays. We cannot feel the magnetic fields of a distant neutron star. We cannot perceive the seismic vibrations of its crust. But through the tools of science and the creative translation of data, we can create analogs that allow us to experience these phenomena through our existing senses. There is something profoundly moving about hearing the voice of a magnetar, the rhythmic patterns of its vibrations translated into sound waves that we can directly experience. It creates a connection across 50,000 light-years of space, across the gulf that separates our human scale from the cosmic scale, our earthly experience from the exotic physics of a neutron star's surface. Imagine listening to this strange cosmic music, the translated vibrations of SGR 180620 filling your ears with patterns that originated in one of the most extreme environments in our galaxy. The sounds are alien, unfamiliar, unlike anything produced by natural processes on Earth, yet they represent something real, something physical, actual oscillations in the crust of a distant, incredibly dense stellar remnant, transmitted across half a galaxy and across the conceptual divide between the directly experienced and the scientifically inferred. In this act of listening, of experiencing a translated version of a distant cosmic event, we find another form of connection, not just intellectual understanding, but sensory engagement with phenomena far beyond our direct reach. We cannot visit a magnetar. We cannot survive its intense gravity, its lethal radiation, its powerful magnetic field. But through these translations, these bridges between the cosmic and the human, we can experience aspects of its reality, can know it not just through equations and models, but through our embodied senses. As you imagine this experience, this listening to the translated voice of a distant magnetar, allow yourself to appreciate the multiple layers of connection involved. The physical connection through the actual photons that traveled from SGR 180620 to Earth. The technological connection through the instruments that detected these photons and translated their patterns into other forms. The conceptual connection through the scientific understanding that allows us to interpret what we're hearing. And the emotional connection through our human capacity for wonder and appreciation. In these layered connections, these bridges across physical and conceptual space, we find a unique form of relationship with the cosmos, neither purely objective nor purely subjective, but a creative synthesis that allows us to know what lies beyond our direct experience while acknowledging the translations and transformations involved in that knowing. As we continue our exploration of SGR 180620 and its giant flare, let us consider yet another dimension of this remarkable cosmic event, the philosophical questions it raises about perception, existence, and the nature of physical phenomena. One might ask, if the giant flare occurred in the perfect silence of space, with no medium to carry sound waves, can we meaningfully say that it made a sound at all? If a magnetar flares in the vacuum of space, and there's no air to carry acoustic waves, does it make a sound? This is not merely a play on the old philosophical question about falling trees and absent observers. It points to something deeper about how we understand and categorize phenomena that lie outside our direct sensory experience. The giant flare from SGR 180620 released enough energy that, if it had occurred in Earth's atmosphere, it would indeed have created the loudest sound ever experienced in human history. Yet in the vacuum of space, this same energy created no sound whatsoever, only electromagnetic radiation, gravitational waves, and other forms of energy that propagate through vacuum. Is it meaningful, then, to describe the giant flare as loud or as a roar, as is sometimes done in popular accounts? Or does this linguistic choice reveal something important about how we, as humans, relate to phenomena beyond our scale and direct experience, through metaphor, through analogy, through translation into terms that connect to our embodied understanding of the world? These questions touch on fundamental issues in the philosophy of perception and the philosophy of science. How do we know what we know about distant objects like magnetars? What is the relationship between our scientific models of such objects and their actual nature? To what extent are our descriptions shaped by our particularly human perspective, our specific sensory capabilities, our evolved cognitive tendencies? There are no simple answers to these questions, no definitive resolutions of the tensions between objective reality and subjective experience, between the phenomena themselves and our necessarily limited and translated understanding of them. But in exploring these philosophical dimensions, we gain a richer, more nuanced appreciation of both the magnetar itself and our relationship to it as knowing beings. Consider the multiple translations involved in our understanding of SGR 180620. First, there is the translation of its physical emissions, primarily gamma rays, X-rays, and other forms of electromagnetic radiation, into electrical signals within our detectors. Then there is the translation of these electrical signals into digital data. This data is further translated into visual representations, graphs, spectra, images that scientists can analyze. The patterns identified in this analysis are translated into mathematical models and physical theories, which are then translated into language, technical papers, conference presentations, popular accounts that can be shared with others. At each stage of this process, something is preserved and something is lost or transformed. The original gamma rays carry certain information about the physical processes that created them, but not all of this information is captured by our detectors. The digital data records certain aspects of the detector's response, but not the full context of the observation. The visual representations highlight certain patterns while potentially obscuring others. The mathematical models capture certain relationships while necessarily simplifying the full complexity of the phenomena. The verbal descriptions communicate certain aspects of understanding, while inevitably falling short of conveying the complete mathematical or visual comprehension. This cascade of translations, this series of transformations from the phenomenon itself to our human understanding of it, is not unique to magnetars or to astronomy. It characterizes all of science, all of human knowing. We never have direct, unmediated access to reality as it exists independent of our perception and cognition. We always experience the world through the filters of our sensory systems, our cognitive architecture, our conceptual frameworks, our linguistic categories. Yet, and this is crucial, this recognition of the mediated nature of our knowledge need not lead to radical skepticism or to the conclusion that we cannot know anything about reality. The success of scientific predictions, the consistency of findings across different methods and perspectives, the convergence of multiple lines of evidence, all these suggest that our transformed understanding captures something real, something that exists independent of our perception of it. The giant flare from SGR 1806-20 was detected by multiple instruments on different satellites, observed by astronomers using different techniques, analyzed through various mathematical approaches. The consistency across these diverse methods and perspectives suggests that the flare was not merely a construction of our observational techniques or conceptual frameworks, but a real event with objective properties that our various translations have captured. However imperfectly, let this philosophical exploration rest gently in your awareness as you continue to drift through this cosmic narrative. There is no need to resolve the tensions between objective and subjective, between the phenomenon itself and our understanding of it. Instead, we can hold these different perspectives in creative tension, appreciating both the reality that exists, independent of our perception, and the necessary role of our human perspective in how we come to know and relate to that reality. In this philosophical space, this recognition of both the reality of what we study and the inevitably translated nature of our knowing, we find a balanced perspective that neither claims more certainty than is warranted nor abandons the possibility of genuine understanding. It is a middle path that honors both the magnetar in its own right and our human capacity to reach across 50,000 light-years of space to know something true about this distant, exotic object. Now, as we continue our exploration of SGR 1806-20 and its giant flare, let us consider the question of scale. Not just the physical scale of the event itself, which we've already explored, but the scale of its significance relative to our human concerns, to the grand tapestry of cosmic phenomena, to the ongoing evolution of our galaxy and universe. From one perspective, the giant flare was an event of tremendous significance, the most powerful flare ever detected from a magnetar, an event that released more energy in a fraction of a second than our sun will emit in 250,000 years, a cosmic explosion that briefly outshone almost everything else in our galaxy. It challenged scientific models, provided new data about exotic states of matter, and reminded us of the extreme forces at work in our universe. From another perspective, it was merely one more energetic event in a universe filled with such phenomena, less powerful than a supernova, less consequential than a gamma ray burst from a collapsing star, less influential in the long term than the steady radiation from millions of ordinary stars that sustains life and drives cosmic evolution. In the grand scheme of cosmic history, stretching billions of years into the past and potentially trillions of years into the future, the giant flare was but a momentary flash, a brief perturbation in the generally smooth flow of energy through our galaxy. Both perspectives are valid. Both capture something true about the relative significance of the event. The tension between them, between seeing the flare as extraordinarily important or as cosmically mundane, reflects a broader tension in how we understand our place in the universe, in how we assign significance to phenomena at scales vastly different from our own. Consider the scales involved in the giant flare from SGR 1806-20. The magnetar itself is perhaps 12 miles in diameter, smaller than many major cities on Earth. Yet it contains approximately 1.4 times the mass of our Sun, which itself contains 99.8% of all the mass in our solar system. The energy released in the giant flare, though enormous by human or even solar standards, represents only a tiny fraction of the total energy stored in the magnetar's magnetic field, which in turn is only a small portion of the total energy contained in the magnetar itself through its mass energy equivalence. The flare traveled 50,000 light-years to reach us, a distance of approximately 300 quadrillion miles, or about 30 million times the distance from Earth to the Sun. Yet this represents only about half the diameter of our galaxy, which itself is just one of billions of galaxies in the observable universe. The observable universe, in turn, may be just a tiny patch of a much larger, or even infinite cosmos, most of which lies forever beyond our observational horizon due to the finite speed of light and the expansion of space. In terms of time, the initial spike of hard gamma rays lasted only about 0.2 of a second, a brief moment even by human standards. Yet the after effects continued for minutes, hours, days, and years, with the radio afterglow still detectable months after the event. The energy from the flare spreading outward at the speed of light will continue to travel through space essentially forever, though becoming increasingly diffuse and difficult to detect against the background radiation of the cosmos. As you consider these nested scales, these overlapping temporal and spatial dimensions, allow yourself to feel both the vastness of the cosmos and your connection to it. We are small within this vastness, our lives brief compared to cosmic timescales, our concerns perhaps insignificant from a universal perspective. Yet we are also part of this cosmos, made of matter forged in ancient stars, capable of detecting and understanding phenomena like the giant flare from SGR 1806-20. Despite their enormous distance and exotic nature, there is both humility and dignity in this recognition, humility in acknowledging our small place within the cosmic expanse, dignity in recognizing our remarkable capacity to comprehend it. We need not claim cosmic significance for our species to value our unique perspective, our ability to witness and understand events like the giant flare, to translate the language of gamma rays and magnetic fields into concepts that human minds can grasp and appreciate. In this balance of humility and dignity, smallness and connection, we find a cosmic perspective that neither inflates nor diminishes our place in the universe. We are neither the center of cosmic significance nor meaningless accidents in a purely mechanical cosmos. We are rather conscious participants in an ongoing cosmic drama, witnesses capable of translating the physical into the meaningful, of finding patterns and beauty in the dance of energy and matter across space and time. Let this balanced perspective rest gently in your awareness as we continue our exploration of SGR 1806-20 and its giant flare. Feel the peaceful coexistence of cosmic scale and human significance, of objective physical processes and subjective meaning-making. In this balanced awareness, this gentle holding of apparent opposites, we find a perspective that honors both the magnetar, in its exotic power, and the human capacity to know and appreciate it across vast distances of space and conceptual understanding. As our journey through this cosmic narrative continues, let us consider the legacy of the giant flare from SGR 1806-20, how this brief but incredibly energetic event has influenced scientific understanding, theoretical models, and perhaps even our philosophical perspective on the cosmos. Though the flare itself lasted only moments, its effects on human knowledge and understanding continue to unfold even years later. In the realm of astrophysics, the giant flare provided an unprecedented opportunity to study magnetar physics under extreme conditions. Prior to this event, theoretical models of magnetars had suggested that such powerful flares might be possible, but the actual observation of one allowed these models to be refined and tested against real data. The detailed observations of the flare's initial spike, its oscillating tail, and its radio afterglow provided constraints on models of neutron star structure, crust composition, magnetic field configuration, Hand emission mechanisms. One of the most significant scientific impacts involved the study of the quasi-periodic oscillations detected in the tail of the giant flare. These oscillations, interpreted as seismic vibrations in the magnetar's crust, allowed a form of asteroseismology, studying the internal structure of a neutron star through its vibrations, similar to how geologists study Earth's interior through seismic waves. The precise frequencies of these oscillations provided information about the stiffness of the crust, the strength of the magnetic field within different layers, and potentially even the state of matter at various depths. This information, in turn, fed into broader questions in nuclear physics about the behavior of matter at densities far beyond what can be created in terrestrial laboratories. The interior of a neutron star represents the highest density of matter that can exist without collapsing into a black hole, making it a unique laboratory for testing theories about the strong nuclear force, the equation of state of nuclear matter, and the possible existence of exotic phases like quark matter or strange matter. Beyond these specific advances in magnetar and neutron star physics, the giant flare also influenced how astronomers think about other high-energy phenomena in the cosmos. The recognition that magnetar flares can release such tremendous energy in such brief periods led to reconsideration of the possible sources of at least some short gamma-ray bursts, brief but intense flashes, of gamma radiation that had previously been attributed primarily to neutron star mergers, or black hole formation. If magnetar giant flares in distant galaxies could mimic the B signature of these more exotic events, then careful analysis would be needed to distinguish between different sources of short gamma-ray bursts. This realization led to the development of new analytical techniques and observational strategies designed to differentiate between various potential causes of these energetic cosmic flashes. The giant flare also highlighted the importance of maintaining and expanding our global network of space-based observatories capable of detecting and characterizing such events. The fact that multiple satellites captured different aspects of the flare, some measuring the gamma-ray spectrum, others tracking the X-ray emission, still others monitoring the radio afterglow, demonstrated the value of a diverse, complementary suite of instruments for studying transient cosmic phenomena. In the years following the giant flare, new space observatories were designed with enhanced capabilities for detecting and analyzing similar events. Improved detectors, wider fields of view, faster response times, and better coordination between different observatories all emerged as priorities for the next generation of high-energy astrophysics missions. The giant flare had demonstrated both the scientific value of such observations and the limitations of existing instruments, spurring innovation and new approaches. Beyond these practical scientific impacts, the giant flare also influenced how we think about the dynamic nature of the cosmos. Before the era of modern high-energy astronomy, the universe might have seemed relatively static on human timescales, stars shining steadily, galaxies rotating majestically but imperceptibly, cosmic processes unfolding over millions or billions of years. Events like the giant flare from SGR 1806-20 reveal a more dynamic reality, where enormous energies can be released in fractions of a second, where the seemingly quiet night sky conceals violent processes occurring throughout our galaxy and beyond. This recognition of cosmic dynamism, of the universe as an active, energetic system, rather than a static backdrop, represents a significant shift in perspective, not just for professional astronomers, but for anyone who contemplates the nature of the cosmos. The night sky becomes not merely a collection of steady light sources, but a dynamic landscape where magnetar flares, supernovae, gamma-ray bursts, and countless other energetic processes continually reshape the cosmic environment. Let this awareness of cosmic dynamism, of the active, energetic nature of our universe, rest gently in your consciousness as you continue to float through this narrative. The stars may seem fixed and unchanging from our brief human perspective, but in reality, they live, evolve, die, and sometimes, as in the case of SGR 1806-20, undergo sudden, dramatic transformations that release enormous energies into the surrounding space. There is something both unsettling and reassuring about this recognition. Unsettling because it reminds us that the cosmos is not a stable, unchanging environment, but one where sudden, unpredictable events can release tremendous energies. Reassuring because it places our own experiences of change and transformation within a cosmic context, reminding us that growth, evolution, and sometimes dramatic reconfiguration are fundamental aspects of existence at all scales. As we hold this awareness of cosmic dynamism, this recognition of the giant flare as one particularly dramatic example of the active nature of our universe, let us also consider how our understanding of such events shapes our philosophical perspective on time, change, and the nature of physical processes. The giant flare from SGR 1806-20, with its almost instantaneous release of enormous energy, followed by a gradual decay back to quiescence, offers a striking example of nonlinear dynamics, of systems that can build up energy gradually but release it suddenly, of tipping points and thresholds, of catastrophic reorganizations following periods of apparent stability. Such nonlinear dynamics appear throughout nature, from earthquakes to avalanches, from forest fires to financial market crashes, from epileptic seizures to societal revolutions. In studying the giant flare, scientists are not just learning about this particular magnetar, or even about magnetars in general, but about a broader class of physical processes that share certain fundamental characteristics, despite occurring in vastly different systems at widely varying scales. The mathematics of sudden energy release, of critical thresholds, of system reorganization applies across these diverse phenomena, revealing underlying patterns that connect seemingly unrelated aspects of our world. This recognition of common patterns across different scales and systems represents one of the most powerful aspects of scientific understanding, the ability to see unity in diversity, to recognize how the same fundamental principles can manifest in different forms across the cosmos. The giant flare from SGR 1806-20, in this sense, is not just an isolated astronomical curiosity, but a particularly dramatic example of processes that occur throughout the natural world. By studying such extreme examples, where the fundamental principles are expressed with particular clarity and intensity, scientists can refine their understanding of the underlying dynamics, developing mathematical models and conceptual frameworks that apply not just to magnetars, but to a broad range of complex, nonlinear systems. The insights gained from analyzing the giant flare might thus inform understanding of other phenomena, from the dynamics of Earth's magnetic field to the behavior of plasma in fusion reactors, from the mathematics of sudden phase transitions to the modeling of complex networks. As you consider these connections, these patterns that link the exotic physics of a distant magnetar to more familiar earthly phenomena, allow yourself to appreciate the intellectual beauty of such unifying principles. There is something deeply satisfying about recognizing how the same mathematical relationships, the same physical laws, the same underlying patterns can manifest across such diverse scales and systems. Ferd suggests a cosmos that, for all its diversity and complexity, exhibits a profound underlying coherence, a mathematical elegance that connects the very large with the very small, the exotic with the familiar, the distant with the near at hand. This recognition of underlying patterns, of mathematical relationships that transcend particular manifestations, has been one of the most powerful drivers of scientific progress throughout human history. From Newton's realization that the force that pulls an apple toward Earth is the same force that keeps the moon in its orbit, to Einstein's insight that gravity can be understood as the curvature of space-time, to modern efforts to unify the fundamental forces of nature, scientific advances often involve recognizing connections, similarities, and patterns across phenomena that might initially seem unrelated. The giant flare from SGR 1806-20 contributes to this ongoing process of pattern recognition and unification, offering an extreme example of processes that occur in milder forms throughout the cosmos. By understanding the physics of such dramatic events, scientists gain insight into the broader dynamics of energy storage and release, of magnetic field reconfiguration, of nonlinear system behavior across a wide range of contexts. Let this awareness of underlying patterns, of connections across scales and systems, bring a sense of intellectual coherence to your understanding of the giant flare. It is not merely an isolated curiosity, but part of a broader tapestry of natural phenomena, linked to other processes through shared mathematical relationships and physical principles. In studying this extraordinary event, scientists are not just learning about one particular magnetar, but about the dynamics of complex systems throughout the cosmos. As the energy from the giant flare continues its journey through space, spreading outward at the speed of light in an ever-expanding sphere, the silent void gradually returns to its usual state. The magnetic field of SGR 180620, partially reconfigured by the massive energy release, establishes a new equilibrium. The crust, its seismic vibrations gradually damping out, settles into a slightly different configuration than before. The storm of particles accelerated during the flare disperses into the surrounding space, their energy gradually merging with the ambient cosmic ray background. In this return to quiescence, this restoration of relative calm after a moment of extraordinary activity, we find another cosmic pattern, the oscillation between stability and change, between gradual evolution and sudden transformation, between the quiet accumulation of energy and its dramatic release. This rhythm, this cosmic breathing of tension and resolution, plays out across scales from the subatomic to the galactic, from nanoseconds to billions of years. As our exploration of SGR 180620 and its giant flare draws toward a close, let us widen our perspective once more, imagining the magnetar not as an isolated object, but as part of the broader tapestry of our galaxy, one particularly exotic thread in a vast cosmic weaving that includes hundreds of billions of stars, countless planets, nebulae, black holes, and other wonders both known and yet to be discovered. From this expanded viewpoint, the magnetar appears as one expression of the creative diversity of cosmic evolution, one possible outcome of a complex chain of events beginning with the formation of massive stars from primordial gas, continuing through their brief but brilliant lives as they fuse lighter elements into heavier ones, culminating in spectacular supernovae that scatter these newly forged elements into space, while leaving behind exotic remnants like neutron stars, magnetars, and black holes. This cosmic cycle of creation, transformation, and renewal represents one of the most profound patterns in our understanding of the universe. The elements that make up our bodies, the carbon, oxygen, nitrogen, calcium, iron, and other atoms essential for life, were forged in the hearts of ancient stars and scattered by ancient supernovae. Some may have passed through phases where they were incorporated into neutron stars or even magnetars before being ejected back into the interstellar medium, eventually to be incorporated into new stars, new planets, and eventually into living systems capable of contemplating their own origins. There is a certain poetry in this cosmic recycling, this flow of matter and energy through different forms across billions of years. The atoms in your body have histories that stretch back to the earliest generations of stars in our galaxy. They have been part of cosmic dramas that include processes as extreme as those occurring in SGR 180620. They have traveled across vast distances, been part of countless different systems and structures, before temporarily coming together in the particular configuration that is you, reading or listening to these words, contemplating the distant magnetar and its giant flare. In this recognition of our physical connection to the cosmos, our material kinship with even its most exotic objects, we find yet another form of relationship with SGR 180620. We are not merely distant observers of this strange and powerful object, but are, in a very real sense, composed of matter that has been shaped by the same cosmic processes that created it, governed by the same physical laws that control its behavior, part of the same galactic ecosystem that includes both the seemingly familiar and the exotically extreme. As you rest in this awareness of cosmic kinship, this recognition of your place within the grand cycles of cosmic evolution, allow yourself to feel both the vastness of space and time that separates you from SGR 180620 and the underlying unity that connects you to it and to all other parts of the cosmos. This balanced perspective, acknowledging both separation and connection, both difference and kinship, offers an integrated view that honors both the unique specificity of each cosmic entity and the shared origins and principles that unite them. In the quiet after the storm, in the peaceful silence that follows even the most energetic cosmic events, we find a space for reflection on the nature of the universe, on our place within it, on the remarkable fact that we exist in a cosmos capable of creating both magnetars, with their exotic physics and conscious beings capable of detecting, studying and appreciating them from across vast gulfs of space. As the night deepens and the stars continue their silent wheeling overhead, imagine SGR 180620 continuing its slow rotation, its powerful magnetic field once again contained, its energy building gradually toward perhaps another giant flare in the distant future. Imagine the radiation from the 2004 flare continuing its journey through space, an expanding sphere of information about that brief, intense moment still propagating outward, perhaps to be detected by observers around distant stars millennia from now. And here on Earth, as you drift gently in this cosmic narrative, imagine the quiet continuation of human curiosity, of scientific exploration, of our collective effort to understand the universe in all its complexity and wonder. The story of SGR 1806-20 and its giant flare is not finished, not because the event itself continues, but because our understanding of it continues to evolve. Our appreciation of its significance continues to deepen. Our perspective on its place in the cosmic tapestry continues to expand. In this ongoing exploration, this never-completed journey of understanding, we find a fitting metaphor for our relationship with the cosmos as a whole, a relationship characterized not by final answers, but by ever-deepening questions, not by complete comprehension, but by expanding wonder, not by reaching an endpoint, but by continually discovering new horizons, new mysteries, new opportunities for growth and understanding. Let this awareness of the ongoing nature of exploration, of the never-complete character of understanding, bring a sense of peaceful openness to your contemplation of SGR 1806-20 and its giant flare. There is no rush to final conclusions, no pressure to achieve complete comprehension, only the gentle unfolding of awareness, the quiet deepening of appreciation, the peaceful recognition of both what we have come to understand and what remains mysterious. As we drift through the silent vacuum of space in our imagination, having witnessed the aftermath of one of the most powerful single events ever detected by humans, let us carry with us both the specific understanding we have gained about this particular magnetar and its extraordinary flare, and the broader perspective it offers on the nature of the cosmos and our place within it. The stars will shine long after we are gone, their light crossing endless space. But tonight they shine here with you in silence. May your evening be calm and your rest be deep. And perhaps in your dreams you might visit SGR 1806-20, witnessing from a safe distance its tremendous power and exotic beauty, a quiet observer of one of the universe's most extraordinary objects, a conscious participant in the ongoing cosmic story that includes both magnetars with their incredible forces and human minds with their remarkable capacity for understanding, appreciation, and wonder.